Good day, ladies and gentlemen. My name is Boris Fedulov, and my report is about construction plate enforced by metamaterial elements. So the question is, we have now so interesting tools for design structures as optimization, we call it usually topology optimization. So if we need to choose for some kind of criteria structure, this algorithm helps us to redistribute our material in the most optimum way. And we have here blue color means we don't have material, and red color means 100% of material. 100% of material means 100% of stiffness. And this picture, this movie that you see, it is different stages of optimization. So how it usually works, we divide our solid body into many subregions, and each subregion has its own volume and it has its own density parameter. And then we connect this density parameter with stiffness like this, and then we redistribute our densities in the material to meet the purposes and criterion we want to get. For example, here is the minimum of compliance, which is which means that we going to have maximum stiffness and with restriction to mass, so we cannot spend 100% of material. We need to put only, for example, 30% of initial material, 50%. And it's a very pretty well-known, well-developed tool for design of structures. So why we still use in construction works this simple and very old idea of reinforcement of our construction plates? We use simple steel bars with simple orientation, all to 0 or 0 and 90 degrees, and that's all. Maybe we can get something from our new design tools. We can get some improvement to this process, to this construction, to these structural elements. This is the idea of this research. For this purpose, we took the plate like this, and we applied two types of loads. It's two independent load case, bending in this way, bending in this way. This is the most critical loadings for floor plates, where we put them horizontally in our building. This is the main load case for this kind of plate. And we have two independent load cases, and we can summarize two independent compliances for minimization and minimize them together for first load case and for second load case. Okay. And here is the result of optimization. We can see it's two layers, two outside layers, and something in the middle, very difficult structure. The result, the algorithm was asked to keep 10% of initial weight of the reinforcement of structure for reinforcement, and we get this result. So you can see different stages of optimization. And the idea is we of course cannot perform this exactly this shape of the geometry, optimized geometry, but we can get main idea and the whole idea of research. The main idea of the structure is to take angled sticks like this, these rods, we can just realize like these simple sticks, and we have some supports like pyramid shape. And the idea to get this structure, remove conventional reinforcements and replace it with these structural elements, which are inspired by this optimization analysis. So here again we can see some stages of optimization. This is how plate will look if we use this structure, and we will fill this plate with concrete inside, and these small holes will show us that we already filled this area in the process of filling of liquid concrete inside the plate. Okay, so to compare this conventional plate with this one, we would like to perform numerical experiments. For numerical modeling, we choose classical plasticity with one Mises criterion for metal parts, and for concrete we choose Drucker-Prager plasticity criterion. Here is how it looks like. So it's Mises stress multiplied by the function which is linear to triaxiality parameter, so we can get a stronger limit in case of compression and weaker in case of tension. And here is the function of equivalent plastic strain. As equivalent plastic strain, we use here the work spent on plastic strain, and for failure criterion we use criterion proposed by Kolmogorov. Here we have integral over equivalent plastic strain, and it is divided by the function of triaxiality parameters, so we can adjust the result for tension and compression. For example, tension we can accumulate during tension loading, we can accumulate more damage, and during compression we can accumulate less damage. And so totally we have three parameters that we can have to determine experimentally for concrete, of course. So here is a table with properties what we used to calibrate the model. We can see that we can use different failure strain in tension and compression using this Kolmogorov criterion. So okay, so we are going to model this, the most critical case for floor plate. So the problem statement formally looks so we have rigid elements here. It is rigid tubes. We apply load here, fix these two tubes, and we put a plate here and check what failure we have, what failure load we have in this case. And here with the result is final frame, result of modeling, the final frame of modeling before total failure of conventional plate. So we can see that some concrete elements destroyed and removed from the analysis, and we can see reinforcements inside. It is reinforcements modeled by means of beam elements, and interaction between concrete and beam elements realized through embedded elements technique, which is usual for abacus, for example. Okay. This is the view of the modeling of proposed plate. So we can see it is 1/4 of this plate because of symmetry. Even as we can see that we have smoothed plasticity over bottom layer of our reinforcements. Okay, and here's the comparison of these two structures. In case we have the same metal consumption, like 170 kilograms for 1 cubic meter of concrete, blue line, it is conventional result for conventional plate, and the green line, it is a result for our proposed plate. We can see that we have much higher strength, and if we reduce our metal consumption almost 2 times, we can see, and this is a red curve, we can see that we have almost the same loading curve and the same strength, but it's 2 times less of metal spent on this structure. So we can say that we almost doubled the strength, and optimization works. So some words about how to produce this plate. So it seems like it is difficult, but using modern laser machines, it is really affordable, because all procedures are very standard. We can do laser metal cutting, then some stamping, and then laser welding. And especially interesting feature of new modern machines that we can do one side welding. That's why we can produce these plates essentially easy. And this plate has some very remarkable features. The weight and the stiffness and the bending. It is hard to destroy completely this plate, because when we get failure in one cell, we usually destroy one cell. The load just redistributed to the rest of the cells, and it is not like in case of conventional rods, when we destroy one stick, a lot of material of the plate doesn't work in this case. But here only one small cell will be removed, so durability is high. And another thing that usually failure what we can get in this type of structure is buckling of one edge of the pyramid. But in case if it's filled with concrete, it is almost impossible, because surrounding concrete supports them and prevent buckling. So that's why probably the secret why it's so strong in comparison with conventional plate. Okay, so thank you for your attention, and one more time you can see what is inside this interesting optimization result of plate. We just removed the outer top surface. Thank you one more time.